So hello, thank you so much for coming on time. So we have Dr. Professor Chuchu Fan with us. She's an assistant professor at MIT. She's done a lot of amazing work in verification and also in learning and control. She's also won quite a few awards, including an NSF Career Award too. So today she'll be talking to us about neural certificates and autonomous designers. Please.
All right, great to see everyone here. So you might see my title is slightly different from the one I sent to Abraham. Sorry about that. I thought maybe some of you might be interested in the large language model work that could generate some interesting thoughts here. So I plan to still spend most of my time talking about neural certificate. It's a piece of work that we have invested a lot in the past few years. And large language model is kind of like building the connection there to see how we can use all these technologies we have developed for let common users, human language users, to access these tools to solve problems in large-scale autonomy design. And thanks for the introduction. This is Chuchu. I'm an assistant professor. If I come 2 months later, I'll be associate professor at MIT, and just very close to you, 10 minutes of walk. You're more than welcome to visit our lab or come here to have a discussion. So with that, let me get started. So my talk will be divided into 2 parts that you will see they are actually quite closely connected. So we are motivated by solve these difficult problems in safe control or safe navigation problems, and mostly for robotic systems. And of course, there are tons of challenging problems that people are looking at. And within those, we are particularly interested in a few. But for example, how can we simultaneously control a super large fleet of agents? So in this background is one of the simulation environments that we have developed. You can see it's like a city, like Cambridge type, but it's a virtual city. And these tiny white dots here are the drones. So the question I have is, if we imagine in the future that we want thousands or tens of thousands of drones to help us deliver stuff around the city, how would we even make sure they will perform their job, they'll fly to their destinations on time and safely with respect to high-dimensional spaces, including both high-dimensional state and input space. So state for complex systems, their state space could be huge, and we all know for control problems, a large state space could cause an issue. And the input space is when we talk about perception-based control, or sometimes people use pixel or LiDAR point cloud to directly control the system. Then the input space we are facing is very large compared to the traditional control problem we are looking at. How do we guarantee safety in these cases? How would we handle the unknown or imprecise systems or environment models? And how would we provide assurances and guarantees? So these are the problems we're looking at. And the approach we are looking at now is called neural certificates. So if you have never heard about it, it's actually not different at all from the traditional control certificates that you have learned in any of your control classes. For example, the Autonomy function, if you work on control, you must know the Autonomy function is a mathematical certificate that people build to show that the system is stable. Stable in the sense that there is a fixed point. Some people call it an equivalent point, or there are many names here, but the system, however you perturb it or you start from a different location, it will all converge to this equivalent point. And the way to prove that the system has such a stability guarantee is to providing the Autonomy function. And if you work on safety problems, you probably have worked on barrier functions. It is similar to the Autonomy function, but it creates a barrier to tell you which is safe, which is unsafe, what's a barrier between them, and how to make sure you always stay within the barrier. And a lot of people call it this barrier like invariant set or forward invariant set. All these concepts in control kind of relate to the same thing. And if we manage to find a barrier function, we can show the system stay within a safety set and prove safety. If you work on very agile robots, you may want to look at contraction metric. It's also similar to Lyapunov function, but now it's like a differentiable version to make sure your system, like the quadrotors or your racing cars, can track a particular dynamical trajectory instead of just converging to a fixed point. So all these things, they're definitely not developed by me. I think the Lyapunov function came maybe more than 100 years ago. And contraction metric is by Professor Jean-Jacques Slotin at MIT. If you took like the nonlinear control class or read his textbook, he developed the contraction metric. He brought that up back in the 1995. So since we have all these very powerful tools in control, we can provide or certificates or assurance for the desired system properties. And we don't have to stick to one at a time. There are actually ways to combine all these different things together. We can do stability and safety. We can do safety and tracking, or all of them together. There are ways of merging this certificate together. Now, what is the issue here? Unfortunately, up to today, there's still no general approach that can tell us how to find these certificate functions. If you work on linear systems, there are a lot of ways, but we all know linear systems are very well studied. But if we work on nonlinear systems, especially those that have that high dimension, or those that cannot be described using simple dynamics like polynomials, there's basically not a single good way to find these certificate functions. So that is the line of research we're doing with today, I'm going to just look at one particular type of certificate that tend to solve a lot of interesting challenges I just mentioned. But before that, I want to quickly give you an overview in case you're interested in this newer certificate and what it can do. Over the years, my lab, Reliable Autonomous System Lab at MIT, has developed a sequence of tools, algorithms, open source, GitHub repo that contain everything I'm going to talk about today about newer certificates. So, and I also have some references next to the bullet points I have here. We have shown that newer certificate can help with single agent certified learning-based control. Oh, by the way, neural certificate means we want to use neural networks to represent those certificate functions. And at the same time, we want to find the controllers that obey those certificate functions. And there are like, it's actually the concept is not that difficult, but there are different versions of neural certificate we can develop. For single agent system, we can make it robust, we can make it verified, and we can make those be used online and adapt to changing environment. Compared to, for example, receding horizon-based control, this is much faster and can also provide a higher level of assurance. It can generalize to a very large fleet of agents, and that will be the topic I will bring up right after this. It can handle high-dimensional state and input space and large dynamic models. And it can be combined with reinforcement learning for you to use regular reinforcement learning tools, but what you can have is not only a policy, but also a certificate function. And it can also provide some insights on how other uncontrolled agents can react to autonomous agent. Like how would we model the mental models of human when they are interacting with an autonomous agent. So I have some references there. Feel free to let me know which part you would like a little bit more discussion. But for the rest of the first half of the talk, I would like to show you why we love neural certificates and how it can generalize to a super large fleet of agents. So with that, let me tell you the problem setup first. So we're looking at this multi-agent navigation problem. So on the left here, it's an animation showing you the problem. We have a bunch of agents. They're represented using the orange dots, and they want to go to their destinations. And each of them is already assigned a destination. This is a low-level control problem. And next part, I will show you a little bit about how to assign that destinations. But for now, let's assume each of them have a destination. And you can see if they are not at their destination, they will have a line connecting them to some green dots. Okay. And what they don't know each other in the environment unless they are very close to them. So if the two agents are close, you will see a black line connecting them. That means now they're able to communicate. They're able to talk. They can send whatever they want to each other. And we leave that part very flexible. to explore different types of tasks. But you can see, like, if the two agents are far away, they actually have no communication line. So, and this doesn't have to be a distance-based. We chose a distance-based communication for simplicity, but you can choose whatever communication you allow the two agents to have. So overall, they will just form a graph. And there are some unknown obstacles in the environment. So those red rectangles, and those obstacles could move around. And this agent have no clue where these obstacles are. How the way they detect these obstacles are through LiDAR. So they directly have a LiDAR-based control. We didn't show the full LiDAR, but only the LiDAR rays that spin around. So you'll see some thin lines that kind of like going around. They will try to detect where the obstacles, and we will only in the animation only show you the lines that has like detect obstacles. Now that is a multi-agents setting. Let's think about if we have this problem set up, how would we navigate all these agents to their destination while making sure, first of all, they do not bump to the obstacles. And second, they do not bump to each other. And third, they don't trap at a local deadlock. So like in multi-agent cases, you may always say they form some sort of like, they get super congestion at the region, they couldn't get detangled from it. How would we design a controller that will take in this information, the information from LiDAR, the distance to their goal, and also some potential messages from their neighbors, and make sure they will all get to their destination on time and without any collision happened. And of course, there are a lot of approaches, but the approach we want to look at is something that can really generalize. We do not want to design a specific policy for each of them. We want something that can handle the changing neighborhood. You could have zero neighbor agent or obstacles to some large number, and each of these agents will run a similar version of algorithm. But together, there's some overall global guarantee that there to make sure they're all safe and they can get to their destination. And the neural certificate we're developing in this case is called graph control barrier functions. And I will tell you what is graph control barrier function and why it can work. So to give you like just a high level overview of the graph control barrier function, it is a type of neural certificate that is fully distributed. It is trained without even explicitly modeling the environment, the obstacles. It will just run during training. We will just randomly collect some sample points, and this certificate is directly used to monitor the system and produce the safe controllers. So with that, let me give you a little bit of mathematical background of what is graph control barrier function. And this is something new we developed from the traditional control barrier function. From the setup, you can see that the multi-agent system is just naturally a graph. Here, we consider two types of nodes or vertices in the graph. An agent can be a graph, can be a node, and also any point in the point cloud in the LiDAR array that detected can be another node. And you can actually assign a lot of different node in a sense, like you could have one of your neighboring node to be a collaborative node. You could have another neighbor node to be an adversarial node or someone who doesn't want to talk to you. You could have a node that represents a hitting point of the LiDAR array to the obstacles. So anything that represents, either obstacle and agent is a node. And then they can form edges. Here as I said, we can assume there's a sensing this radius. Within the sensing radius, they can see each other, they can talk to each other, or they can see the obstacle. But as I pointed earlier, you can form your own rule of forming the edges. Maybe two agents that are collaborative, they have some form of a communication module on board, they can talk to each other. But that's our graph. Once we have the graph, we can define something called the GCBF, graph control barrier function. And let me just list the three equations, and that will be one of the few equations I will show in my talk today. So GCBF is a function h that will take in two types of input. One is the node and the other one is the edge. And we call those node features and edge features because, as I said, node could be different. It could be a hitting point of the LiDAR, it could be a neighboring agent, and they could have different types, and you use your favorite way of encoding who they are. You could use your integers, you could use other sort of symbols that you like to represent your node, your neighboring node. And the edge means you can now communicate. You can send some information to each other. If it's just a lighter ray hitting point, that means it's very passive. You know the distance and angle to that hitting ray. And if it's another agent, they might be able to tell you their type, their velocity. They could also show you more, like we have a even more recent version of the work. I don't have the slides here. They can even tell you what type of task they have accomplished, to tell you like these tasks that remain unsolved. I have finished those type of tasks. And those are the two input for this GCBF. And the output of this GCBF is just one scalar value. So the scalar value says it is positive when the current agent I is safe, and it is negative when it is unsafe. So that first two is very simple. If you know barrier function, it's nothing different from a traditional barrier function. And that's actually telling us why it's called a barrier function, because h equals 0 is that barrier we're looking for. It is a barrier to tell you you should always stay on the positive side and you never get across a barrier to become unsafe. Now, how would we enforce that safety? How would we make sure the agent will never get across that barrier? Is through the third condition here. So the third condition, let's just look at the first part. The first part said h dot, like forget about the second term. H dot is positive, which means along your trajectory, I only allow h to increase. Then if that's the case, if I'm originally start in the safe place and my h only increase and it would remain safe. That's basically how barrier function works. But that might be too conservative. Thinking about this room is the place I call safe and the walls are the barriers. If I only have h dot to be positive, then I can only stay further and further away from the barrier. I might need to accomplish some tasks, like if two agents meet at the narrow corridor, they will have to first get close and then figure out a way to avoid each other. So we don't just want h to increase, we want h to be flexible as long as h is always positive. That's why we have the second term here. Second term is a class K function. It's basically a monotonically increasing function that is 0 at 0. With this second term, basically what it says here, h dot doesn't have to be positive unless you are already at the barrier. So it means the closer you're to the barrier, the more harsh you should turn around. That's how it works. And that's like basically how barrier function works. Now, what we have shown is if each of these agents has such a distributed graph control barrier function, then the existence of this graph control barrier function on each agent will guarantee the safety or collision avoidance of the multi-agent system from a non-colliding initial condition. So it's kind of starting from a fully distributed mathematical certificate, we can prove the overall safety of the entire multi-agent system graph. And then our contribution is that how would we find such an H? We kind of allow H to be so flexible and to have all these very interesting features. How would we find out the H? And that is the same as the difficult problem I mentioned at the beginning. How would we find these certificate functions? And we naturally, if this is a graph, so very naturally we can use graph neural networks to represent both. So what we do is to use two graph neural networks to represent both these H function, which is a graph control barrier function, and the controller. Now the controller is also a fully distributed controller. That means we can just get one copy of it and put on every single copy of the agent that have the same dynamics or the same node feature. So the way it works is actually pretty straightforward. I have the three conditions for GCBF that we want. And the way to find this H and the controller U is through a backpropagation using a single loss function that encode the three conditions. So I have the color coding here. Each of these following terms of the terms in the lost represent one of these constraints. And they're actually pretty easy to understand. So let's just look at the first one. The first one is that I want H to be positive for the agent that is safe, for the agent's current state that is safe. Then what I do is, if you ignore the gamma here, thinking about gamma just being 0, then the first loss term here is just saying, I want to penalize the case when H is negative, right? When H is negative, then there will be a positive loss. Otherwise, it will be 0. And the other conditions are basically encoded in the same way. And you may wonder, how would I find the controller? You can see in the last condition here, the yellow one, because we need to find a controller to make the third condition valid through the chain rule. Actually, the controller will be trained at the same time. So this single loss function will get us both the GNNH and the graph neural network controller U. And if I look at the architecture, it's basically quite straightforward. It's like a very standard graph neural network way, like architecture, where we will collect the neighbors, node feature, and add feature through the embedding. This is super important. In the embedding part is kind of fixing your changing neighborhood into a fixed length vector as the information and sent to the attention layer. After the attention, then we will separately get to the controller and the neural certificate. So now if I come back to my plot here that I just showed, this is basically a visualization of the graph neural network, graph control barrier function that I just mentioned in the view of this agent here in the center. So there is the 0 barrier would be all these lines you have saying. You can see that they have a connection, or they pay attention to the neighbors that are close to them. And they kind of like, for this agent, they don't have any connection to a neighbor that is far away from them. These orange dots are the agents, and the black dots are the endpoint of the LiDAR. So there's no modeling of the environment. We just randomly sample the hitting points of the LiDAR. That turns out to be a very good way to represent random obstacles that could appear in the environment. And the attention itself can also somehow show how much of attention you should pay to your neighbors. You can see that if from these values, you can see if an agent is closer to them, actually this value is getting larger. So if it's further away, it's closer to 0. And if they're very far, it's 0, means they don't really pay attention to that agent. So this is like a simplified version of how it works. Let me show you more like qualitatively how it works. We trained with, actually in this case, it's an 8 agent. For later cases, 16, but you just need to train with a small group of agents to understand how your neighbors could distribute, okay? And it's not a problem at all if you turns out having more neighbors than the ones, that the number that you have in the training environment, because GNN has this way to form an edge and disconnect with another edge. I will show you some more results in the next few slides. In this first one, trained with a very small number of agents, and you can see how it works. The same controller, the resulting controller, can be deployed on an arbitrary number, theoretically arbitrary number of agents. Here we can go, I think in our experiment, we went all the way to 4,000. And the reason we didn't really go beyond 4,000 was because it takes too much time to run each of these simulations. And it works very well when we introduce more agents to the environment. But this is not a challenging environment, because you can see when we introduce more agents, there will be more space. So you pretty much run into the similar type of neighborhood that in the training environment. We are wondering how well this can generalize, in a sense, for the same space. So from left to right here, we have the same space, this area here, but we just put more and more agents. So you can see at some point these get so crowded. I think this one is with like 128. We can always also go up all the way to 4,000. That would be like super crowded. You can probably tell that in this case, at some point, let's see if I can show you, like it's already getting very crowded and they form a lot of edges. But the results can generalize pretty well. Of course, when we dump more and more agents, will be super crowded. At some point, it takes a lot of time for them to move. We see the results like the safety is always reserved. So the safety rate is always 100%. But when we put more agent, it will take longer time for these agents to get disentangled from this local crowded area and get to their destination.
When you talk about the safety part, the value function right now definition has been converted to a soft constraint, right? When you train the neural network like that.
It's not a soft constraint. So this last term, of course, if it converges, it will be enforced all the time. It's not soft, right? We are not like if it converges, but of course we can discuss what if it doesn't converge because it's machine learning and there are some engineering tricks we have to play. And we have this gamma here. The gamma I didn't really mention explicitly. I said treat it as 0, but here we actually do have a positive gamma to like enforce its constraints to be even more satisfied. And then if we choose appropriate gamma, we can show that even if the algorithm this loss doesn't converge to 0, if it converges to a small number, it can still make sure this is a valid graph barrier function.
So, but don't we need this to hold for all x?
Yes, so you need this to hold for all x, but the thing because each agent has the same copy. So the theory of GCDF can show you if each agent has one of this, and the entire graph will have a global barrier function that satisfies the safety. You have a question?
I have even more simpler question, which is what is being trained and what are the data that are used to train this network? What is?
Yeah, so the data here is basically you will have to start with letting some of the small number of agents to run, and they will collect the information, the trajectories, including your neighbor's node feature and edge feature. And as I said, node feature could be, whomever you bump to, whatever of obstacles you have seen, and also the edge features could include the obstacles that you the points, like the point in the point cloud we have sampled, and also your neighbors, if they are close by, what type of information they want to send to you. In this work, so in the one I just shared, their neighbor will only tell you where they are relative to you. But in a newer version, we have like RNN where a neighbor can tell you what type of environment they have seen along their way and what type of tasks they have accomplished. So those are the information used for training.
So what is HI exactly? Is it a vector?
No, H is a scalar value, right? H will take in the features of your neighbors and produce a scalar value that's positive for when you're safe and negative when you're unsafe.
So the entire network is now the barrier function.
Yes, so the upper part is a barrier function. The lower part will become your controller.
Oh.
Matt, you had a question?
Matt? You have a raised hand?
It's a quick question. How do you generate?
Can you hear me?
Yes.
Oh,
Go ahead.
I'm sorry. So looking at your animations, there are computational geometry theorems about graph locking that say beyond a certain point of density, you basically cannot route some of these. So what is being guaranteed in this setting?
So in this
What are the
setting,
certificates going to guarantee?
in this setting, the certificate guarantees safety. So that's why I was saying if we dump more and more agent at some point, like the local crowded area cannot be resolved. Now, that's a very good question. That's related to the nominal. So I do have a nominal here. The nominal, so what the barrier function is to make sure the system is always safe. We do need a nominal. Sorry, I didn't mention that. The nominal here is basically what the agent is originally trying to do. Now, in this case, in the animations I've shown, the nominal controller is just a controller that drive the agent in a straight line to their destination. So there is like the agent already have some sort of controller to drive them to their destination. And this barrier function will chime in when this like action could be unsafe, they will do a perturbation to the nominal controller to make sure it's always also safe. So it's definitely possible that, because the GCBF can only guarantee safety, then there will be cases when there will be like a local deadlock. It's not solvable at all. And then this agent will just get trapped there, and some of them will not be able to reach their destination. That's something we have observed. And we also observe that in this case, if we add some sort of a small disturbance to these agents, they might be able to get like them unsolved, like they might be able to detangle from that local deadlock, but there's no mathematical guarantee on the line in saying they will definitely get out of the deadlock.
Okay, thanks. Sorry to interrupt whoever was talking.
Does that answer your question as well?
I think I have a question as well.
Mhm.
Do you incorporate collision avoidance and deadlock resolution in the same mechanism or?
Yeah, so we do not actually have an explicit deadlock resolution algorithm here. It's the deadlock part is going to be a matter of luck if that small perturbation can get that deadlock resolved. But that's something we are studying. So we actually have extended work looking at how to incorporate more deadlock resolution algorithms here. So the easiest starting point would be introducing some sort of a deadlock resolution at the nominal controller. But I think that would be a harder problem to bring in here. That's definitely something we're looking at.
Quick question.
Mhm.
How do you tune the class K function?
The class K function. So the class K function currently in our setting is all just linear. So it's like a constant multiply h. That constant itself is a parameter that is learned in the framework. But we can explore more interesting class K functions, and you can introduce like a polynomial, and then those coefficients can become something that is going to be learned in the entire framework. Okay, so and then you can also see with this one has the obstacles and lidars. It seems like on the right hand side they still perform pretty robustly when there will be local congested area, and so far they could still resolve that congestion or the deadlock by themselves. But there are cases we have. I don't have the curve here, but we have the more quantitative results. And you will see that when we have more and more agents, the safety rate is always very good, but the reaching rate will start to drop when we have more agents. That's because we don't have a good deadlock resolution solution here. I want to quickly ramp up this part with a few hardware demonstrations. The thing we are very happy with this algorithm is it's super easy to implement. We have this crazy fly, the palm-sized drone, and ask them to kind of like switch their locations. In the bottom case here, they not only switch their location to form some sort of formation, but also we have an intruder. I'm not sure, like this is maybe background is too dark, but there is an adversarial agent that is just trying to, like it's a student holding another drone trying to disrupt this formation, but the other agents, they act pretty robustly to this adversarial agent. Let me see if I can point you to the adversarial one. I think this is the one that one is the one that's like trying to interrupt the other agents. And we could also do the same mechanism can be used for docking. So we have some platforms here. These drones will need to take off and then find a new platform to land. Of course, the docker will start to move around and will be able to, it's also a safety problem. They need to precisely land to their corresponding platform. And the bottom here is another demonstration that we collaborated with Lincoln. They want to have like some sort of a surveillance job where two drones they have to stay very close. So collision avoidance, it can be seen as one type of safety, and connectivity is a similar type of safety. So in this case, we don't say safety means the distance has to be above something. We can give a range of distance. That means they should stay they should stay some distance with each other, but they also have to maintain that distance to be small so they can talk to each other. In this case, these two agents, they have to stay close and they are performing like a surveillance around a circle. There is an adversarial spot that is moving around, and what the drones are trying to do is to stay outside of the site of the thing by the spot. And all this, if you come to my lab, we can easily show this demonstration to you by clicking just basically a run button, and it works very robustly. We also, of course, for hardware, we didn't have that thousands of robots, but in simulation, we actually have the simulation environments I brought up at the beginning for different type of robots. It's the same city. We're looking at the city part, the seaport, where we have all the autonomous forklifts that move around the cargo. And we also have the boats. We have some corner to do the stress test to see what if all the agents get so like crowded at the corner, can they get resolved of this situation by themselves? And we have also implemented a LiDAR-based control. I won't have time to go into the detail of this. This is basically a reinforcement learning algorithm. We have a way to have this graph barrier function into a reinforcement learning algorithm that I originally planned to talk about, but I'll be happy to if you're interested in this part. And this is an F-16 that's mimicking what Maverick is doing in the Top Gun movie. If you have seen the second Top Gun, instead of a Maverick, we actually have a LiDAR to fly this F-16 through this narrow corridor. The F-16 has never seen this corridor before, and it has to maintain a very low altitude. If you have seen the movie, you will know like all the enemies radar on the top here. So the airplane will have to stay very low. And this is a F-16 model by the Air Force. So it's supposed to be, it's a 17-dimensional Simulink model. And we add a LiDAR on top of it. We believe, in the movie, they said Maverick is, the success rate is pretty slim. So Maverick is pretty much the only person who can do this. And even if it's not guaranteed, he can always do that. But we have seen, like in our case, the success rate has been pretty high. And in this reinforcement learning framework, we can even show that if we cannot find a controller, then such a controller doesn't even exist. It's not feasible to fly the F-16 through such an environment. But again, I'll be happy to talk more about the discussion here. But I bring up this video trying to show the framework can handle very complex dynamics. This is a 17-dimensional airplane model, and it's not even described using the traditional ODEs that we are familiar with. It's like if you ever work with Simulink models, they are blocks and lookup tables and some weird models that we don't even know what's going on. And you click on it, you open up another, network of blocks, and you open up one, there's like multiple layers before you see what is ultimately implemented there. So that is the first part of the thing. I do know like we have to stay on time. There is another line of work we are working on that look at a slightly higher level of the problem, but how large language models can play a role here. I would like to spend a few minutes to talk about that work, just in case some of you might be interested in large language models. Okay. All right. So what motivated us is the higher level of the robotics problem. Like at the neural certificate work, we are looking at the low-level control. Now, basically, you can see all these agents, they all have a clear objective. They have a goal they want to reach. They have some safety mechanism they have to maintain. But when we actually look at the robotic system that we're interacting with daily, we actually want the robot itself can understand what we want them to do. So left here, if I'm not sure how many of you have seen this movie, it's called The Bicentennial Man. Back in 1999, there's a robot whose name is Andrew, and he's like a household robot coming to your home to do the maintenance and do the housework, cleaning. And the movie was about how the robot Andrew started with someone who can interact with human, do your daily job at your home, and Andrew slowly adapt to like a real person. But if we just look at the picture that people have about interactive robots many years ago. We want the robot to be able to exactly understand what we want them to do. At the same time, they will obey all the basic safety rules. But if we look at all the robots that are being used, I'm not saying this is a state-of-the-art technology, but the robot that people widely accept are either pre-programmed and running in the environment without human, or they can only perform some very simple tasks, like cleaning up the floor, or they are teleoperated. They can do pretty complicated tasks, but it's not autonomous. How would we go from this type of robots to the robot that we can interact with? We have to solve a bunch of challenging problems. One of them is definitely the problem of robot language grounding problem in robots. Basically, if we say our requirements in English, how would we ground those natural language into something that's computational or can be computed in the robot? And there are like, I want to be slightly fast here. Over the years, there are like tons of different approaches being developed, all the way from developing a symbolic representation to learning-based approaches. Each of them have their pros and cons. For example, for symbolic way, it's very precise, but it's very hard to capture the nuance of the natural language, and very difficult to generalize to the different type of language that people use. For the learning-based approach, we are facing all these challenges that machine learning are facing. So in recent years, you probably, especially the past year, you probably start to see a lot of works on large language models, how to use large language model to design the robot interaction part, how to use large language model to do the control. Large language model, of course, may help address a lot of the problems in the robot planning. For example, it's very good at generalizing to the new context and the new language structure that was not there in the pre-training stage. It can help with scaling language grounding technique to very complex sentences and can be deployed in a very diverse set of field. And this picture here I have here basically shows a lot of people's belief. They believe if we plug in a large language model like a GPT-4 or even the newer version, then the robot will become an actual robot we desire. They will understand everything we say, and they will act in the way that we will appreciate. But can we actually directly use large language models to solve a lot of the robot planning problems? Thinking about just the problem I brought up at the beginning. So each of these robots, now we have a good way to navigate them to their destination. But now my question is how to assign the destinations. So the task allocation or destination assignment problem itself can become a problem, something called the shortest path or traveling salesman problem. If you have learned hard about traveling salesman problem, it says, I have a salesperson who need to visit a sequence of locations. Now I have to decide what's the order for this robot, for this salesperson to visit this, what's the order of this destination they have to visit to have the minimum cost, because it takes some cost to get there. So the task allocation is basically a multi-agent version of the traveling salesman problem. You will see that large language model is going to be terrible if you ask it to solve a traveling salesman problem or shortest path problem, because large language models are not optimization tools. The way they respond to the neighboring environment is based on the probability that is derived from their training data. And this is fundamentally different from the combinatorial optimization problem that we are looking at in the robot planning domain. If we look at how people are using large language models these days, for example, this work, if it's called by Google 2 years ago, they are one of the first group who brought large language models into robotics. They said, for this example says, if I spill my Coke, I ask a language model, can you help me clean it up? And what they expect the large language model to do is to propose a sequence of actions so the robot can just execute. Now, it's possible that these actions are not executable. Then there will be some feedback getting back to the large language model saying this action is not feasible, can you propose something else? And this line of work, the most representative one is the bottom one here called SECAN. It has attracted a lot of attention. The title is Do As I Can, Not As I Say, and by Google. has tracked a lot of follow-up work. And they also have some similar work trying to ask large language models to directly output the code that the robot is going to execute. So if we look at this work, none of them are using large language model to solve a combinatorial optimization problem. They're using it to provide a common knowledge as a task planner. It's basically step-by-step instruction. And so how would we bridge the gap there? This line of work we are looking at is to teach a large language model to use the tools that we have developed. Things like the neural certificate tools that we have used, but in this initial version of the work, we actually teach a large language model to use a planner for the task and motion planning problem. And how would we ask a large language model to use the tool? We have to build something, have the intermediate parts, the intermediate language. And the intermediate language here we're using is called temporal logic. I'm not sure how many of you have heard about temporal logic. It's okay if you have never heard about it. But our idea is to use an intermediate language to connect large language models with the very powerful planning tools that we have developed and enable an autoregressive loop to be in the hope to break this dilemma in human-robot interaction. So we have all the traditional planning algorithms that are rigorous and explainable, but they're terrible in terms of scalability. And we have the new learning-based approaches like reinforcement learning, large language models. They're good at scaling to a much more complicated environment, but they are not rigorous and explainable. So this work we're trying to do is to bring this, different advantages in the different domains together to have something that is both rigorous and explainable at the same time that can generalize. So let me give you like a 2-minute quick overview of what is temporal logic. If you've never heard about it, as I said, it's okay. The framework doesn't really heavily rely on temporal logic, but the idea of how would we teach a large language model to use tools to solve problems that are difficult for common users. So temporal logic is a rigorous system of rules for the requirement engineering, or sometimes people call it specification engineering. It can capture many complex requirements like in spatial, temporal, and logical constraints. And it's definitely not something that we brought up. It's been there for more than 4 decades or 5 decades. And it's part of the IEEE standard in many domains like electronics or aerospace. The father of temporal logic actually won the Turing Award back in 1996 because temporal logic has enabled a lot of specification engineering in the EDA domain. And why we want to use temporal logic here is because it's a high-level specification language. It tells the robot what to do, just as human, we tell the robot what to do, not how to do it, because the how to do it part is the optimization problem. What to do is a high-level specification we wanted to have. And another reason we want it, since it's a high-level language, how can we directly use them? Over the years, researchers, including our lab, has developed a lot of tools that can directly generate the motions and tasks for the robot from temporal logic. For example, look at this toy example where I want this robot to travel to the blue region, that's the destination. Now, in this case, the low-level control won't be able to solve it because you can see the robot basically cannot, because they are trapped. There are walls, there are doors. So this problem cannot be handled by a low-level control because now the robot will have to pick up the key to open the door before it can find a path to get to the destination. And this is kind of like a mobile game where the keys are stored somewhere. You have to figure out where the keys are stored and then open the corresponding door. And most likely you will have to find out all the keys and open the doors in a certain order. So I have the requirements here, again, color-coded. The robot should reach their destination, cannot travel through the wall and the closed doors, and must visit the corresponding numbered region to find the key, then open the door and be able to travel there. So this is not something we can use like a control language to describe, but instead we can use temporal logic. The bottom here, I'm not going to show you all the syntax of temporal logic, and you don't have to read it. But the bottom here, my point is a very concise but precise way to describe all these requirements I have. And if they are high-level requirements, it says you get to your destination, you cannot travel across the wall, and you cannot open the door until you find out where the key is. And they precisely reflect all the requirements I have here. And I have a slightly more complicated example showing like it's a search and rescue job. We have a certain number of drones we want to send out to multiple locations. We do not want to tell the drones where they should go, but they should figure out a way to visit these locations. Even complex formulas like this, they are temporal logic formulas over the entity, quantity, time, and event. And they should be precisely captured using something at the bottom here. And first of all, we have developed a lot of efficient planning algorithms that can plan the motion for the robots to solve this temporal logic requirements even with good guarantees. We have the optimality guarantee. So our algorithm can have probably optimal computational complexity to solve puzzles, like I mentioned. And it can also generalize in the sense that if we embed this traffic rule in each of this car that we want to design, for example, we embed the collision avoid and collision rule, the stop sign rule. It's quite complicated. At stop sign, you have to first pause, and then you look at whether it's your turn. When it's your turn, you should pass that intersection very quickly. Or if it's a traffic light, you have to observe the traffic light. So these rules are embedded into each of these agents. But if we put a larger number of agents at many intersections, all these, you can see all these agents, they cooperate very nicely because they all satisfy these rules, and together they will maintain the safety, and each one of them will make sure they satisfy the rule, even if there are other agents like the red agents, they are not having the rules embedded. They are just randomly going around. But you can see the blue ones, the ones we embed the temporal logic specification, can follow those requirements. Now with that, what we have is, once we have the temporal logic, we can find the motions and assign the tasks for the robot nicely. But how would we go from this type of natural language description to a temporal logic that can precisely describe the task? That might be something that the large language model can do it for us. So the idea is quite simple. We will use large language model with this temporal logic-based task and motion planning tools to solve natural language-based time problem. So the framework works like the following. We have the language instruction, for example, like the puzzle I just described. And we have the state observation. These two types of input will be sent to a large language model. A large language model will translate everything into a temporal logic specification. Now, next, the temporal logic will be consumed by a planner. Planner will tell us what to do. That's a very natural process, but there are you will have a lot of doubts immediately. How would we guarantee that large language model will translate everything precisely? What if anything goes wrong? So that is the main part of this framework. We actually have the autoregressive reprompting technology here. What we do is basically inserting two types of checkers. The first is a syntax checker to check whether the translated temporal logic is grammatically correct. And that is very easy to check. It's basically checking the grammar. If anything is translated into a syntactically wrong temporal logic, we have a way to automatically tell the large language model this part of the translation is wrong and generate a new prompt to ask you to find a new temporal logic. And even if we're given a grammatically correct temporal logic, there's no guarantee that it correctly reflects what we want. So we have a semantic checker that will further take the intermediate plan that's given by the by the planner and basically check for the alignment of the result with the user requirements. If there's any misalignment, they are going to automatically generate a prompt to tell the large language model this part went wrong and you should fix your translation. And hopefully it will converge to a final thing. And in the process, we could also ask a human to give us feedback if this is just not feasible. I will show you a very interesting example where human feedback can be useful here. But this is basically the whole framework. The way we use it is to use large language model as a translator and checker instead of asking it to solve the task allocation problem. Now, with that, we can actually solve these interesting puzzles or the household work using natural language that we have. I'll be super fast here just to show you like how the result can get improved. If we plug in this framework called AutoTamp, the large language model as checker and translator into the GPT-3 and 4, we can see the success rate actually jumped from 0% or less than 10% to pretty high, especially when we have the hard constraints on timing and the geometric constraints. The first line of work, some other approach, basically this task planning and feedback, it's very similar to SECAN, ask large language model to tell you what to do next. But they don't ask it to satisfy any hard constraints. Temporal logic here basically enforce all these constraints that we care about. And we can also do multi-agent thing if you have ever played Overcooked game. It is a typical example where you need multiple levels of, the ingredient will have to be cooked for a certain amount of time in the right order. You have to serve the customer before they get angry. And in the Overcooked game with GPT-4, actually this framework can achieve 100% success rate for actually pretty huge number of Overcooked game levels. We can do the multi-agent surveillance, like very similar to the one example that I gave. And as I said, so in this whole framework, we do not ask the user to know anything about temporal logic. It's actually completely hidden from the interface. All interaction with human are through natural language. The temporal logic there is to enable some sort of a self-reasoning to understand whether this plan that is generated is correct. And they will check for the automatic alignment. They will try to fix the bugs that are introduced if there's anything went wrong. Another similar application that doesn't use temporal logic, but the same framework, is a travel planning problem. So thinking about when we design like plan for our next vacation, it's actually quite complicated combinatorial optimization problem. If I need to travel, I spend a lot of time searching online. I have this time window that I can travel. I have this much of a budget. I have these locations I want to go to. All these complicated constraints together will have to let me like search on the website for multiple, information. I collect this information, discuss with my family. So this is a similar problem. Can we accomplish a travel planning problem with large language models? The short answer is it's not possible today to use large language models to plan your travel. There's a group from, let me show you here. There's a group from a couple of universities. They proposed a benchmark called Travel Planner. This is a benchmark for real-world planning problem, travel planning problem with large language model agents. And they have 1,300 different user queries for different type of travels they want to plan. And the conclusion I got was state-of-the-art large language model cannot handle such complex planning problems. And the GPT-4, as the best one of them, can only have a successful rate of 0.6%. So over the 1,000 queries, GPT-4 could only find 6 or 7 successful plans that satisfy all the user requirements. But if we bring back the framework I just mentioned, what we do here is we still have the natural language, and we translate these constraints not into a temporal logic anymore, but just how the constraints are described, send it to a different solver, not the robotic solver, but we send it to an SMT solver. I can show you that our successful rate jumped directly from 0.6 into approaching 99% for GPT-4 and Cloud 3. And of course, we also tested the open model called Mistral. This is the Cloud 3 and GPT-4, they are closed models, or people call it, I don't know, like the giant, closed source models. Mistral is one of the best open source models that are available. And even for Mistral, the success rate is very good, like 85%. And not only it can, this framework can resolve this complicated travel planning problem, because of the feedback it can provide, we can actually interactively tell people no, your constraints are not satisfiable, your current travel, require is not feasible because of the following reason. And are you willing to modify that part? For example, if like this, because all the interaction are through natural language, it will be very easy to communicate. Like this user query want to ask the framework to plan a trip from Paris to, I don't know where this place is, for 3 days within this time window. And large language model, this framework will be able to identify the reason because the user only want to take the nonstop flight. But we can identify the reason, tell you nonstop flight is not possible because there's no direct flight between these two cities. So it will suggest that you remove the nonstop flight constraint. The user can choose to take it or not. If not, for example, the user can say, I don't want to remove the nonstop flight constraint, but there's no flight. What the framework can do is to now I actually find another city, which is London, that almost satisfy all your other constraints. But are you willing to change your destination? The user may say yes, or they may say no, and there will be more interactions between the user and this framework to eventually converge. So they will identify whether your budget is not enough, your time window is not the best one. If you want to, eat certain type of food, there's a better location we can tell you. So together, this framework is almost the same as the one I just described, but you just plug in a different solver. They can now solve the travel planning problem. We believe that we can actually bring different types of solvers here that we have developed to allow users to solve different type of interesting constrained combinatorial search problem. So that's everything I want to talk about today. Very briefly, I talk about graph neural networks that we have used to build a graph control barrier function for a fully distributed or decentralized, scalable and generalizable collision avoidance control. And the second part, I apologize for rushing over that part. It can be combined with domain-specific tools to allow natural language as input for robot planning problem and also, travel planning problem. And there'll be more applications for using this type of technologies we have developed. So we have, I have a QR code for my group, but you can also just type realm.mit.edu. Everything we have done is open source. Everything I've mentioned today, you should be able to find it on the website. And I will spend a little bit more time this afternoon here. If you're willing to talk about anything, I'll be happy to do that. Okay, thanks. Sorry for running over for the